Hi, my name is Eunsuk Kang. I am a assistant professor in S3D at CMU. And today I want to tell you about one type of software analysis called invariant-based reasoning, which can be used to show that your system behaves in a desirable manner. So what is invariant? Invariant is a type of system property that is expected to hold in every step of execution. So examples of invariance may say things like, your drone stays at least 5 meters away from other nearby drones, or that a Facebook profile is only visible to the friends of the user, or that the browser application never runs out of memory, or that no two processes in the operating system should be able to acquire a critical resource at the same time. So let me give you a more concrete example. So here is a navigation robot that moves around a 2D dimensional map. And there are 4 different actions that can be performed by the robot. So at any point, the robot can move in one of the 4 diagonal directions. So the northwest, southwest, northeast, and southeast. And we're going to assume that the robot starts in the location 2-1 in its initial state. Now, we would also like to make sure that the robot never runs into an obstacle. So in this case, the obstacle is located at 3-3. So we want to make sure that the robot ever reaches there. Now, one possible invariant they can come up with for the system is that at any location or at any point in the robot's movement, if you sum up the x and y coordinates, there's always an odd number. And if you can show that this invariant holds, then we can also show that the system will always satisfy the safety requirement because the robot will never run into the location 3-3. Okay. So now the question is, how do we do this? How do we show that this invariant always holds? So one approach to do this is through testing, where we run the robot under many different scenarios and check whether the invariant holds over those scenarios. Now, one problem with this is that in general, there's an infinite number of scenarios you can test, and therefore, it doesn't matter how much testing you do, we'll never be able to tell for sure whether the invariant holds. So another approach that we're going to explore is a technique called mathematical induction. So we're going to use induction to prove that the invariant holds. And there's 3 steps that are involved in this process. In step 1, which we call base case, we're going to show that the system in its initial state satisfies invariant. In step 2, which is the inductive case, we're going to show that for every action of the system, if the invariant holds before the action, then it's also going to hold after the action. In other words, each action of the system preserves the invariant. And in the last step, if you can show that the first 2 steps hold, then based on the principles of induction, we can conclude that the system indeed satisfies the invariant over every possible state. So going back to our example here, let's start with the base case. So in the initial state, we know that the robot starts in the location 2-1, where if you sum up those numbers, that's an odd number. Therefore, we know that the invariant holds in the initial state. In the inductive case, we want to show that each action of the robot preserves the invariant. And at high level, the proof is very straightforward. We know that the robot's going to start in a position whose sum is odd number. And because the robot can only move in one of the 4 diagonal directions, we also know that the sum of x plus y can only change either by 0 or 2. And therefore, x plus y will always also remain odd after each action. So if we can show these 2 steps to be true, then based on the induction principle, we can also conclude that the invariant holds true over every possible state of the system. In other words, the robot is never going to reach 3-3, which contains the obstacle. So takeaway from today's lesson is that first, an invariant is a desirable property of the system that is expected to hold over every execution step. Second, induction is a powerful technique that can be used to show that the system satisfies invariant. And lastly, invariant-based reasoning can be used to show or design systems that must behave in a safe manner. And if you're interested in more details, there's a link to the course at the bottom, and I'll be happy to answer any questions. Thank you.